In this video, we're going to be talking about differential equations. Now, there are two courses in mathematics that focus on differential equations, and we're not going to go that deep into it. We just want to discuss what a differential equation is and talk about a couple of basic techniques for solving these kinds of equations. In my classes, we'll also work a Python program using Euler's method to solve a differential equation. So let me share my screen with you and we'll get started. When we talk about a differential equation, we want to define them and talk about what exactly we mean by a differential equation. Now, some people call it diff-EQ, the course, and some people talk about differential equations as DEs, which is just an abbreviation. Basically, a differential equation is some kind of equation involving a function which is not known. So the function f of x, we write and represent with the variable y. So y represents this unknown function f of x. And in the equation, we also have one or more of its derivatives. So y prime, y double prime, y triple prime, something like that. So a solution to the differential equation would be some function y, which is probably a function of either x or t, that satisfies the differential equation when the function and its derivatives are plugged into the differential equation. So when they're substituted in. So let me give you an example of what a differential equation looks like. So we can see what one looks like right here in the center. This is 3y double prime minus 3y prime plus 5y equals 0, where again, y is representing this function f of x, which is unknown. Now you could write it with f of x, but it's more writing and it's more common and more usual to see it written in terms of y. But of course it does mean the same thing. This is 2 times f double prime minus 3 times f prime plus 5 times the function. So we're trying to find the function f of x or y that when we substitute it and its derivatives into that equation, we get a true statement. So the left side would be 0 and the right side would be 0. So that's what we mean by solving a differential equation. So again, the solution is a solution for the differential equation if when you plug it in, you get a true statement. And a lot of times we're only allowed to say that it's an solution over some interval. So sometimes we get a restriction. This solves it over the interval between x between here and here. Now, a solution to a differential equation may not be unique. There could be more than one function that will solve the differential equation. And in fact, we'll see an example of this later today. So let's now talk about what singular solutions are. Singular solutions are solutions that don't depend on the value of the independent variable. Now, usually the independent variable in a differential equation is either x or t, and usually t is representing time. Now, the singular solution may not match, in fact, probably won't match, the form of the general solution. Remember, we said there's more than one solution. So for most differential equations that we can solve, we can find a general solution for it. However, singular solutions are solutions to the differential equation that don't have the independent variable in them. So the trivial solution, y equals 0, is often an example of a singular solution. Now, y equals 0, of course, is just the horizontal line, y equals 0, and it does not depend on x or t. Let's now take a look at example 1. It says, show that the trivial solution, y equals 0, solves this ordinary differential equation. So ODE stands for ordinary differential equation. And we'll talk about what an ordinary differential equation is in just a minute. We'll define the term ordinary. Right? So first off, we have 2y double prime minus 3y prime plus 5y. Well, y equals 0. So what is y prime? Well, what's the derivative of 0? 0. And what's the second derivative of that? Still 0. So basically, we have 2 times 0 minus 3 times 0 plus 5 times the function itself is 0. And of course, that is a true statement because the left side reduces to 0 and it equals the right side, which is also 0. So the solution y equals 0 does solve this. It's a trivial solution and called a singular solution because it does not depend on the independent variable, which is actually not even mentioned up here. So we don't know whether it's x or t. Let's take a look now at the next example, which is example 2. In example 2, we want to show that y of x equal to x to the negative 3/2 is a solution to this differential equation, 4x squared y double prime plus 12x y prime plus 3y equals 0, provided that x is strictly positive. All right, so we have a restriction on it. Now, writing y of x, of course, is just another way of representing the function. Y is equal to some function f of x, so really this is x to the negative 3/2. Now remember, the negative drops it down into the denominator, and the 3/2 power, of course, is the square root of something cubed. So this is really the square root of x cubed, and now you should see why we have this condition that x needs to be strictly positive. It's in the denominator, so it can't be 0, and it's under a square root, so we don't want a negative value. We want the solution to be real. So we want to show that this is a solution to that, and the first thing we need to do is find the first derivative. So we're going to find y prime by taking the derivative using the power rule. So we get negative 3/2 x to the negative 5/2. And then we take the derivative of the first derivative to get the second derivative. So that would give us a negative 5/2 times the negative 3/2 times x to the negative 7/2, subtracting one more from the power. Now, the negative 5/2 times negative 3/2 gives us a positive 15/4. So we can represent this as 15/4 x to the negative 7/2. And you could, of course, represent them in their radical form, but probably it will be easier just to leave it in its power form. Now we want to substitute these expressions into the differential equation and see if it does result in a true statement, that the left side becomes 0, so it equals 0 on the right. So we go ahead and substitute each of those values in. So we have 4x squared times 15/4 x to the negative 7/2 plus 12x times negative 3/2 x to the negative 5/2 plus 3 times y, which is x to the negative 3/2. Remember, that was given up here. And we're trying to prove that, in fact, that does equal 0. So that's what we're after, is to show it is 0. So the 4 cancels the 4. And when the bases are the same, you add the power. So you need a common denominator. So 2 can be written as 4/2. So you have 4/2 minus 7/2, which is a negative 3/2. So I have 15 x to the negative 3/2. And then I've got 12 divided by 2, which is 6. And 6 times negative 3 will give me a negative 18. So I know the constant is negative 18. And then I have x to the first times x to the negative 5/2. First, I can write as 2/2. 2/2 minus 5/2 is also x to the negative 3/2. And then, of course, the last one, I don't need to simplify that. It's already as simple as it's going to get. And of course, we're trying to prove that that gives us 0. Now, these are all like terms because they're all constants multiplied by x to the negative 3/2. And 15 minus 18 is negative 3, and negative 3 plus 3 gives me 0. And that means that it does, in fact, solve the equation. I get 0 equals 0. So it is a solution to that equation. This differential equation, which is given in terms of the original function y and its first derivative y prime and its second derivative y double prime. But notice it also has the independent variable x in it. It may have it in there, it may not. So it just depends on the differential equation that we're looking at. Let's go ahead and take a look at the next example. This is exactly the same differential equation that we had in the previous problem. 4x squared y double prime plus 12xy prime plus 3y equals 0 for positive x values. But this time we want to show that this equation here also is a solution for it. So in other words, the solution to this differential equation is not unique. There's more than one. So we follow the same process. We first need to find y prime and then y double prime. So to find y prime, we apply the power rule. So we have -3/2 times -9x to the -5/2. And I'm going to leave things in power form. And then I have -1/2 times 7x to the -3/2, right? Which I can simplify this as 27/2 x to the -5/2 minus 7/2 x to the -3/2, right? So the next thing we need to do is find y double prime. So far, I know what y is. I just found y prime, and now I need to find y double prime. So I'm going to take the second derivative of what I just found, which is going to give me a -5/2 times 27/2, and then reduce the power again. So I get x to the -7/2 minus a -3/2. Well, I better make that a plus. Make this a -7/2 x to the -5/2. I chose to leave the negative on the 7/2, and that made the sign in the middle be positive. But again, it's going to end up positive because a negative times a negative gives us a positive. So simplifying this, let's see, 5 times 27 would be 135, and it's going to be a -135 over 4, x to the -7/2, plus 21 over 4, x to the -5/2. And now we need to substitute this into our equation, which is right here. So let's go ahead and substitute that into our equation. And we'll see if this copy paste works. Sometimes it does, sometimes it doesn't. Oh, it's freaking out on me. Let's give it just a second and see if it'll behave. There it goes. So now we have the equation pasted down below. So let's go ahead and substitute our values. And let's remind ourselves of what y is. Y is this expression right here. So let me copy that one, and hopefully this doesn't freak out quite so much. And it just pastes it. All right, so now I've got everything I need. So I'm trying to show that 4x squared times the second derivative, -135 over 4 x to the -7/2, plus 21 over 4 x to the -5/2, plus 12x times y prime, which is 27/2 x to the -5/2, minus 7/2 x to the -3/2, plus 3y, and y, of course, is -9x to the -3/2, plus 7x to the -1/2. And we want to show whether or not that equals 0. So we're trying to prove that it solves this differential equation. And by solve it, we mean that when we find the derivatives and we replace the function with itself, or with its expression, and the derivatives with their values, that it gives us a true statement. So now we need to go through. So go ahead and pause the video, work out the arithmetic and the algebra, and then turn the video back on and compare your answer to mine. Okay, let's see how you did. I kind of color-coded mine. It makes it easier to find like terms. So I went ahead and did 4x squared times y double prime. This is the expression of y double prime, plus 12x times y prime plus 3 times y, and I don't know if it equals 0. That's what I'm trying to prove, that it solves this differential equation. When I distribute these and multiply it out, I get the terms that you see in this row here. I highlighted all the ones that are x to the negative 3/2 terms in blue, and all the ones that are x to the negative 1/2 terms in pink. And then you can see that if you add and subtract the constants at the front, you do get 0x to the negative 3/2 plus 0x to the negative 1/2, which is just 0, which is equal to 0. So indeed, what we found is that this is another solution to this differential equation, the same differential equation as in the previous problem, but with a different solution. So solutions aren't necessarily unique. All right. Let's now take a look at one more for exactly the same differential equation. So this is the same one we've been working with. We found two solutions for it that depended upon x, which means that they're not singular solutions, right? So this is a singular solution because it does not depend on the independent variable. It just has y equal to 0. So it doesn't depend on x. So again, if y is equal to 0, then the first derivative, of course, y prime is 0 and y double prime equals 0. So we get 4x squared times 0 plus 12x times 0 plus 3 times the function itself is 0. And we know that those multiplied together and added together give us 0. So again, it does solve the differential equation. This is 3 different solutions we found. Only one of them was singular. That was the trivial solution, y equals 0. We call y equals 0 the trivial solution because it's not very complicated and it solves many of the differential equations we'll be looking at. Now let's go ahead and talk about how to classify differential equations and what we mean by a general solution as opposed to a particular solution. So a general solution to a differential equation ignores any initial conditions. So sometimes when we solve a differential equation, we only get the solution up to a constant, similar to the constant of integration. And in fact, most times that's where it's coming from. We had to integrate, we got a constant of integration. In order to pin down exactly what the C is, you would need some kind of initial condition, just like we did in Calculus 1. So when we find the general solution, we don't take into account those initial conditions, and then we usually get some solution, maybe up to a constant plus C. But if we take the initial condition into consideration, then we call that solution a particular solution, meaning particular to this initial condition. All right, let's go ahead and classify our differential equations. There are multiple ways to classify, and I'm going to shrink this up a little bit so that we can see it all at one time. So hopefully you can still read this. I'm still sharing my screen with you. There are 3 primary characteristics of a differential equation: type, order, and linearity. Linearity tends to be the one that causes the most trouble for students in detecting. Type and order tend to be pretty straightforward. There are 2 basic types, and these correspond to the 2 courses in differential equations in undergraduate mathematics. There's what's called an ordinary differential equation, which is when there's only one independent variable that derivatives are taken with respect to. So if you only ever take the derivative with respect to x, then we would call it an ordinary differential equation. However, when an equation has derivatives with respect to 2 or more independent variables, then it's called a partial differential equation. Now, you haven't seen these yet. You won't see many of these until you get into Calculus 3, when you start studying functions of more than one variable. In other words, in order to have something that's a partial differential equation, the function isn't just a function of x, it might also be a function of t. And then we can take a partial derivative, and a partial derivative is not written with the straight letter D. It's using this sigma symbol. It looks kind of like a curved back D. So you might say the partial derivative of f with respect to x. And that means, okay, f depends on both x and t, but I only want to take the derivative with respect to x. So I'm going to consider t to be a constant, and I'm only going to take the derivative with x as the variable. Likewise, we could also, since it depends on both variables, we could take the partial derivative with respect to t. In that case, we would consider t to be the variable, and we would hold the x constant, and we would take the derivative as if x were a constant and only t were the variable. So when you see this curved back representation for the derivative, then you know you've got a partial differential equation. It's pretty much a dead giveaway. All right, what about order? Order tends to be pretty straightforward. The order of a differential equation is the order of the highest derivative in the equation. Now, the one that we looked at with 3 different solutions, the highest derivative was the second derivative, so we would call it a second order linear differential equation. And now we get to linearity. This is where students have the most trouble detecting when something's linear and when it's not. When we say linear in mathematics, we don't necessarily mean a line, although it's related to a line. What we mean is that if we consider y, y prime, y double prime, y triple prime, the 4th derivative of y, all the way up to the nth derivative of y. Remember, you have to put the derivative number in parentheses once you get to 4 and beyond. We give up on tick marks and start writing it in parentheses. If you take each one of these and you consider each one of these to be like well, it's not the variable, right? Because x and t or t are the independent variables, but these are dependent variables. They depend upon the independent variables. And to be linear, we can't multiply any of these by each other. So I can't multiply y by y prime or y prime by y double prime. I can't have any products between y or any of its powers. More than that, I can't have composition. So I can't take y and put it inside of y prime, or y prime and put it inside of y. So I can't have any composition of the function with any of its derivatives or vice versa. That won't be okay either. All right, now there's one more condition to be linear. So don't multiply any of the y's by any of the y primes. Don't compose the y with any of the y primes, or compose the y primes with y. And the last one is that the function y and its derivatives cannot be raised to any power other than the first power. So I can't have y squared. If I have y squared, it's not linear. Something that's linear is raised to the first power. And that applies to the derivatives as well. So y prime has to be to the first power. Y double prime has to be to the first power. And we saw that in the example that we did previously. Let's take a quick look again at that differential equation. It's right here. And when you're looking at that differential equation, do you see how while y double prime is multiplied by the independent variable x, it's not multiplied by any other y thing. And y prime is not multiplied by any other y thing. And y is not multiplied by any other y thing. So because of that, and because these are using the prime notation, I know they're ordinary derivatives, dy dx. So keep in mind that, of course, this could be written as 4x squared d squared y by dx squared, using the fractional notation for the derivative. We could write it like this. These are ordinary derivatives with the straight d. All right. So that means it's an ordinary differential equation, and the highest derivative is the second derivative, so it's second order, and it is linear in y. None of the y's are multiplied together, none of the y's are composed together, and all the y's are to the first power. All right. So those are the 3 conditions that we have for being linear. right? No products with the y's, no composition with the y's, and y's can't be raised to anything other than the first power. So now let's take a look and let's go through and classify some. Now, we probably won't classify all of these. That might be a little bit of overkill, but we'll classify some of them, right? So let's take a look at some of these right here, and we can write them down. So let's try maybe the first 5. So let's go down through the first 5 and go ahead and pause the video, work out what you think they are. So remember, we're talking about type, ordinary or partial differential equation, the order, the highest derivative, and whether or not it's linear. And the choice for that is either linear or not linear. All right, so go ahead and work out the first 5 and restart the video and we'll compare answers. So let's see how we did. The first one is definitely first order because of the first derivative. It is nonlinear. None of the y's are multiplied by anything else. And I don't have y prime times anything. And it's an ordinary differential equation. It's nonlinear because I have y squared, right? The second one, I have the first derivative is the highest, so it's first order. I have y prime squared, so it's not linear. But again, they're using the prime notation, so it's an ordinary differential equation. The third equation, I started abbreviating for linear and nonlinear, and I put the abbreviation at the top. I've got the third derivative is the highest derivative, so it's third order. It's not linear because I have y double prime times y prime, and it is an ordinary differential equation. The next one down, the fourth one, y prime times are equal to y double prime plus 3t squared. Second order, it is linear, and it's an ordinary differential equation. The fifth one is written in the fractional form for the derivative, but it still represents y prime equal t, which is going to be first order. It is linear, and it's an ordinary differential equation. Let's look at the next one down, which is also written in the fractional notation. The highest derivative is the second derivative. So let me write that down. So that's going to be second order. Is it linear? Well, I have the first derivative plus the second derivative, but not multiplied, not composed, not raised to powers. So it is linear, and it's equal to 3x to the fourth. And it is an ordinary differential equation because it's a normal derivative with a straight back d. The next one, I've got the first derivative, but it's being squared. That tells me it's not linear. But this is the first derivative here and here, so it's first order. It is not linear, so nonlinear because it's squared, and it is an ordinary differential equation because of the d. The next one is the first partial differential equation that we've seen. So let's look at this next one right here. When we're looking at this one right here, we see that we've got what's called the partial of u, partial derivative. Partial of u with respect to t equal to k squared partial, the second partial of u with respect to x both times. So it's definitely a partial differential equation. We can see it's got a partial with respect to the two different variables involved. This is the second partial derivative. So it's second order. So we do have second order. It is, in fact, linear. Our function here is u, and u is not multiplied by its first or second derivative. So it is considered linear, and it is a partial differential equation, or a PDE, right? The next one down is again going to be an ordinary differential equation. Notice that x now is a function of t. So instead of y, the dependent variable is x. So on this one right here, we have x as a function of t. So x is the dependent variable. So the third derivative, the second derivative, the first derivative. So the highest is the third derivative. So it's a third order. It is linear. and it is an ordinary differential equation. All right. So hopefully this kind of gives you a feel for what you're doing. If you want to take a few minutes, you can go ahead and complete the ones that are on this page. I'll have you pause the video and then turn it back on so you can compare your answers to mine. So let's go ahead and compare and see how you did. You may want to pause the screen so you can check. I just want to point out that the last two down here come up so often in engineering and physics applications and in some other situations that they have names. The first one is called the heat equation and the second is called the wave equation. Yes, this first one does come up in some heat situations. That's where it got the name. And the second does come up in some wave situations. That's where it got the name. But they also come up in other situations not related to heat or waves of some kind. They're just very common differential equations. They're both partial differential equations. Okay, let's go ahead now and let's move on. We want to talk about some more terminology. We want to talk about what an initial value problem is, or an IVP. An initial value problem is a differential equation together with one or more initial values. And by initial values, we pretty much mean a point on either y or a point on y prime or a point on y double prime. So we're talking about an ordered pair pretty much that is on that particular function, y or y prime or something like that. The general rule to be able to fully solve and uniquely solve an initial value problem to get the particular solution, that means that you're not getting a general solution with a C, you're getting the particular solution that fits that initial value, it will be unique, is that the number of initial values needed is equal to the order of the differential equation. So if it's a third order differential equation, meaning you have the third derivative, then you're going to need an initial value for the third derivative, an initial value for the second derivative, and so forth. Well, actually, not the third. You need an initial value for the second, one for the first derivative, and one for y itself. Because what you're going to do, as we're going to see down here, is you're going to solve for the highest order of derivative, and you're going to integrate both sides. So after you integrate y triple prime, you end up with something that's y double prime. And then you'll have a plus c because you integrated, you need the initial value for y double prime in order to figure out what the c value is. So let's go through the steps for finding a general solution for an ordinary differential equation or for solving an initial value problem. Again, as I said before, you want to solve for the highest order derivative by itself. So if you have a y triple prime and you have a y double prime and a y prime and a y, you want to solve for y triple prime. It may help to write it in the fractional form if you find that simpler, and it may reduce part of the differentials when you put it in the integral. Then you want to take the derivative of both sides of the differential equation. So you're going to integrate both sides of the equation, and you're going to use the new order of derivatives initial condition to find the value of c. So for example, if we had a y triple prime and it was equal to a bunch of stuff, we're going to integrate both sides with respect to the independent variable. And when we're done, this is going to give me a y double prime equal to a bunch of stuff with a plus c on the end. And then I'm going to need to know some particular point, some initial value that satisfies y double prime so that I can substitute it in here to find the value of c. And then you repeat the process. You do it again. You're going to isolate the y double prime. You're going to integrate both sides. Now you'll have y prime with a plus c. So you'll need an initial value condition for y prime to pin down that value of c. And then you do it one more time to get the value of y. You'll need one more initial condition for y in order to pin down the last value of c. So this is the basic process of solving a differential equation. Now, there are more ways to solve differential equations. We're just talking about the most basic way of solving a differential equation. We're going to learn basically two different techniques. This is the first technique. And in the next video, when we talk about separable equations, we'll talk about a different technique for solving differential equations of a particular type. Now, of course, in the course that's based on ordinary differential equations, you'll learn many, many different ways of solving differential equations. But in this class, Calculus 2, we're just going to focus on two methods. Let's go ahead and take a look at this problem right here, and let's solve this for the general solution. Now, to be a general solution, because I don't have an initial value, so I won't be able to pin down the value of c. Now, you'll see that this is first order because I have the first derivative. It is linear because y prime isn't multiplied by any other form of y, not composed with any other form of y, and it's raised to the first power. And it is an ordinary differential equation because that's an ordinary derivative. So it might be easier for you if you were to write this one down using the fractional form, which would be dy dx equal to the natural log of x plus tangent of x. So remember, the first thing we want to do is isolate highest order derivative, which in this case, we only have one. So we want to isolate that highest order of the derivative, right? The next thing we want to do is integrate the two sides. So now we want to integrate the left side, dy dx, with respect to the independent variable x. And now we need to integrate the right side. Remember to put the integrand in parentheses, also with respect to the independent variable x. So we integrate the sides. Now, we have to talk about another abuse of notation on the left. You'll see that you've got this dy dx, but the differential is dx. Now, this is an abuse of notation because dy dx is not really a fraction, it represents an operation. And that differential is the bookend to that symbol, which means to integrate with respect to x. But it works, therefore we do it. This is the genius of Leibniz's notation. Yes, you're going to cancel the dx's here. I know that sounds crazy, but it does in fact work. And so you're going to get the integral of dy. On the right side, we split this into two different integrals, the integral of natural log of x dx and the integral of tangent of x dx, right? Now, when you integrate dy, you only have the differential dy now, then the variable is y. And so you should get y back, which makes sense. If I integrate y prime, I should get y. So now I have y on the left side. Now, to integrate the natural log of x, I need to use integration by parts. So this is going to be integration by parts, where I've got u equal to the natural log of x and dv equal to 1 dx. Remember that you can always take the dv part to be 1 times dx, the differential. So we take the derivative of u, which gives us 1 over x. We abuse the notation and swing the dx around. And then we integrate dv to get x. And we choose the particular antiderivative with 0 for the constant to make our life simpler. And then we take u times v minus the integral of v du. So remember the formula, u times v minus the integral of v du. And so this is going to give us x, natural log of x, minus the integral of x times 1 over x dx. Now, the integral of x times 1 over x dx, the x is canceled, so the integral just gives me an x. I'm also going to have a plus c, and I'm going to roll all my plus c's together in a moment. So I get x plus a constant. I still have this equal to y. And now I need to integrate the tangent of x. So if I integrate tangent, remember you need to rewrite it as sine divided by cosine. So this is going to give me the integral of sine of x over cosine of x dx. And I make a u substitution where u is equal to cosine of x and du is equal to negative sine of x dx. And I have the sine of x dx, I just don't have the negative. So sine of x dx is negative du. So I can make the substitution. So I get negative du over u, which gives me, of course, minus the natural log of the absolute value of u, which is cosine of x, plus a constant, right? So hopefully this rings a bell with everyone. And then notice that because I integrated two different things, I have two different constants, but a constant plus a constant is just a constant. So we roll them all together into one big constant. And we say that the general solution is y equal x natural log of x minus the natural log of the absolute value of cosine of x plus a combined constant, all right? If we had an initial condition, I knew that x was some value and y was some value at the same time, then I'd be able to substitute for x and y and be able to solve for c. But in this particular one, we don't have an initial value, so this gives us the general solution. Let's take a look at the next example, which is example number 7. In this one, we're looking for a particular solution, which must mean we have an initial value, and we do. We're told the point -3, -30. So when x is -3, y is -30. That's basically what it's saying, all right? So this is on the original function y. So our differential equation is y prime equal 4x squared. It is, in fact, first order. It is linear, and it is an ordinary differential equation. So I'm going to write the y prime as dy dx. I'm going to integrate with respect to dx on both sides of the equation. And this is going to give me the dx's cancel on the left, and I get the integral of dy. The integral of 4x squared is going to give me 4/3 x cubed plus a constant. And this is going to give me y on the left. So my general solution is y equal 4/3 x cubed plus a constant. That's the general solution. Now I want to use the initial value to find the particular solution. So I'm going to use my initial value, which is -3, -30, to find the particular solution. Right, the unique one. Okay, so this tells me that when y is -30, or rather when x is -3, y is -30. So I substitute those values into the general solution. -3 cubed will give me -27, divided by 3 would give me -9, times 4 would give me -36. So I get -30 equals -36 plus the constant. Add the 36 to both sides. And this implies, of course, that the constant is equal to 6. So then I rewrite the general solution with the new specific value for this initial value problem. And this will be my particular solution. Y equals 4/3 x cubed plus 6. And that's the particular solution to that initial value problem. Okay. Now, sometimes, depending on the type of differential equation that we have, We may already know the form of the general solution. We just want to find a particular solution. So in the next example, we have a differential equation, y equals 3x squared y. So it's first order because of the first derivative. It is linear. None of the y things are multiplied together or composed or raised to a power higher than 1. So, and it is an ordinary differential equation. So this is our first order linear ordinary differential equation. We know that it goes through the point 0, 12. So when x is 0, y is 12. And we're told that this equation right here is a general solution. Y of x equal to c e to the x cubed. So all we need to do is find a specific value of c. So in order to do that, all we need to do now is just plug in the different values. So we're told to use the general solution and the initial value. And we're going to substitute the initial value into the equation. So we replace the y here with 12, and we replace the x with 0. And of course, 0 cubed is still 0, but e to the 0 is not 0. E to the 0 is 1. So this gives me 12 equal to c, right? So then I can rewrite the particular solution as y equal 12e to the x cubed, right? And that would be the particular solution for that initial value problem, right? And if you want to test and see if it works, go ahead and try it out. You'll find that it does indeed work. Okay, we have one more example we want to look at today. That's this one right here. This is a pretty straightforward problem. It gives the initial value in a different format, though. So notice it says y of 0 equals -1. Again, y is a function of the independent variable, which in this case is t, because we have t over here in our expression of the differential equation. It is first order, it is linear, it's an ordinary differential equation. We won't be working with partial differential equations. We'll only work with ordinary ones. So another way to represent this y of 0 equals -1 is to write when x is 0, y is -1. Now it looks just like the previous problems, except that I don't know what form the general solution has. So I'm going to isolate the highest order derivative, which is the first derivative. I'm going to rewrite it as dy dt, and it's equal to 2t. And then I'm going to integrate the left side and the right side with respect to the independent variable, which is t. So I have 2t dt. This will cancel the differential. I know that doesn't really make sense mathematically, but it works. So we do it. And this is sort of the genius of Leibniz's notation. So we have the integral of dy, which gives us y. And this gives us, of course, 2 times 1/2 t squared plus a constant, which gives us t squared plus a constant. That's the general solution. Now, once we have the general solution, we want to find the particular solution using our initial value up here, our initial condition. So we're going to take -1 and replace y. We're going to take 0 and replace t. And that basically implies that c equals -1. And so the particular solution becomes the following. Y equal t squared minus 1. And that becomes the particular solution to this problem. So I hope that this makes sense to you. I think that compared to a lot of the things we learned this semester, this is pretty straightforward and not terribly difficult. What we're going to do in the next section is we'll talk about the method of separating variables. It's a little bit more complicated, but again, not too awful. So I hope that you'll join me for the next video when we take one more look at differential equations.